table of elementary derivatives, we collect in particular the main trigonometric functions. In this video, we unreveal how to obtain such derivatives, starting with the sine function. To study its derivative, we recall two facts. The first is this elementary formula for the sine of the sum of two angles. The second is a well-known special limit. As h approaches 0, the ratio sin h over h, that is in the indeterminate ratio 0 over 0, has a finite value that is 1. Let us now denote the sine function by f and recall that given a value x, the derivative f prime at x is by definition the limit of the difference quotient delta f over delta x as delta x approaches 0, of course when the limit is finite. Here we set delta x equal to h and compute the corresponding variation of f, that is sine x plus h minus sine x. First of all, we exploit the addition formula to write delta f as sine x times cosine h plus cosine x times sine h minus sine x. Isolating sine x in the first and last term, we write delta f in this form. So, dividing by h, we obtain the difference quotient of f as the sum of these two pieces. Now the challenge is studying the limit as delta x, namely h, approaches 0. We have the ratio sin h over h, that is exactly the special limit we met before, so its limit is 1. But since cosine h approaches 1, in the limit h to 0, there is a second indeterminate form 0 over 0 that comes from the ratio cosine h minus 1 over h. Let's see together how to solve this limit. We multiply and divide the ratio by cosine h plus 1, which is certainly non-zero as h is small. The numerator now is cosine h squared minus 1. By the trigonometric identity cosine squared plus sine squared equals 1, it becomes minus the square of sine h. The result is the product of these three terms. As h approaches 0, sine h approaches 0 too. The second term is once again the special limit, so it is 1. And finally, the last term approaches 1/2. Since the limit of a product is the product of the limits when they are finite, it turns out that the limit of our ratio is precisely 0. Back to the difference quotient of f, we are now able to pass to the limit. Indeed, the first term approaches sine x times 0, while the second approaches cosine x times 1. We conclude that the limit exists, and its value is cosine x. Here is how we prove that the function sine x is differentiable at each value x, and its derivative is precisely cosine x. What about the other trigonometric functions? As we will see in a moment, it is no longer necessary to pass through the definition of derivative and calculating limits. All these derivatives can be directly computed by that of sine x, by a simple application of the differentiation rules. For instance, let us consider the function cosine x. Recalling the relation between sine and cosine of two allied angles, it turns out that the cosine of x is equal to the sine of x plus pi over 2. So, the function cosine x can be seen as the composition of two differentiable functions with inner function that maps x to x plus pi over 2 and outer function, the sine. Hence, its derivative at x is given by the chain rule. Derivative of the outer function, the sine, evaluated at x plus pi over 2, that is cosine of x plus pi over 2, times the derivative of the inner function, that is simply 1. Finally, we recognize the allied angles and observe that cosine of x plus pi over 2 is exactly minus sine of x. And here it is the rule for the derivative of the cosine function. Now, Let us see how to calculate the derivative of the tangent function.
Let's compute the derivative of the tangent function. We recall that the tangent is defined as the quotient of sine of x over cosine of x. So, to get its derivative, we can apply the quotient rule. Accordingly, the derivative y prime is given by this rule. Derivative of the numerator, that is sine of x, times cosine of x, minus the numerator, sine of x, times the derivative of cosine, the denominator, must be divided by the square of cosine of x. Let's focus on the elementary derivatives here. So the derivative of sine of x is cosine of x. And the derivative of cosine is minus sine of x. So y prime is equal to cosine of x times cosine of x, that is cosine square of x, minus sine of x times minus sine of x, that is plus sine square of x, divided by cosine square of x. We can write such a quantity in two different ways. The first by using the fundamental trigonometric identity, that is, this is equals to 1. So we obtain 1 over cos square of x, as shown in the table of elementary derivatives. The second way is splitting the fraction. That is 1 plus tangent square of x, which can be useful in some application.
We conclude with the derivative of the inverse trigonometric functions. The proper tool here is the theorem about the differentiation of an inverse function. So, for instance, the arctangent function is defined as the inverse of the tangent when restricted to the open interval minus pi over 2, pi over 2, according to this relation here. A equal to arctangent B means that B is the tangent of A. In the rule for the derivative of the inverse at a fixed value b, we need f prime, that is the derivative of the tangent function, evaluated at a. We have just seen that f prime at a equals 1 plus tangent a squared. But we know that tangent a equals b, so f prime a is 1 plus b squared. All in all, the derivative of the inverse tangent function at b is 1 over 1 plus b squared. Reading x in place of b, this is exactly the rule in the table, which holds true for every real value x. The derivative of the inverse sine and cosine functions can be obtained reasoning in the very same way.